Hello everyone, welcome back to the Network Fixer. This is the channel where we break down complex networking concepts into simple, understandable terms. Today, we are diving into a futuristic topic that's gaining a lot of attention in the networking and security world, and that is quantum networking. You might have heard of quantum computing, but what exactly is quantum networking? And why does it matter for the future of networks? That's exactly what we will cover today. So let's get started. Before we jump into quantum networking, let's quickly recap quantum computing because the two are closely connected. Classical computers, like the one you are using right now, use bits. Bits are binary, meaning they can only exist as either 0 or 1. Quantum computers, on the other hand, use qubits. Qubits can exist in a superposition, which means they can be both 0 and 1 at the same time. This allows quantum computers to perform many calculations in parallel, solving certain problems exponentially faster than classical computers. Two other key concepts in quantum computing are entanglement and quantum interference. Entanglement allows qubits to be linked together, so the state of one qubit can instantly affect another, no matter the distance. The next one is the quantum interference, which lets quantum computers combine possibilities to get correct solutions efficiently. Now, where does networking come into play? That's where quantum networking enters the picture. Quantum networking is the technology that allows quantum information to be transmitted between quantum devices, such as quantum computers, sensors, or communication devices. In simple terms, while classical networks transmit bits or information over cables, fibers, or wireless signals, quantum networks transmit qubits. This opens up new possibilities, especially in terms of security and distributed quantum computing. There are two major goals of quantum networking: ultra-secure communication and quantum internet. When it comes to ultra-secure communication, quantum networks use the principles of quantum mechanics to create communications that are almost impossible to hack. When it comes to quantum internet, a network that can connect multiple quantum devices for distributed computation and collaboration. Let's break down the core concepts you need to understand in quantum networking. The first one is qubits over the network. Instead of sending a 0 or 1, quantum networks send qubits. Because qubits can be in superposition, information can be more complex and powerful. The next key concept is quantum entanglement. Quantum entanglement is the backbone of quantum networking. Entangled qubits share a special link, so measuring one qubit instantly affects the other, even if they are miles apart. This is used in quantum key distribution, which we will discuss shortly. The next key concept to consider is quantum teleportation. Sounds sci-fi, but this is a real concept. Quantum teleportation allows the state of a qubit to be transferred from one location to another without physically moving the particle itself. This is essential for transmitting quantum information securely. The next key concept is quantum repeaters. Classical repeaters amplify signals to cover long distances. For quantum networks, we use quantum repeaters, which preserve the entangled state of qubits across long distances without losing their quantum properties. Together, these components form the foundation of quantum networks. Now you might wonder, how is quantum networking different from traditional networking? When it comes to data type, classical networks transmit bits, whereas quantum networks transmit qubits. When it comes to security, classical encryption relies on complex math. Quantum networks use quantum mechanics, making it nearly impossible to eavesdrop without detection. When it comes to error detection, in classical networks, Errors can be checked and corrected using parity or CRC checks. When it comes to quantum networks, they rely on quantum error correction, which is much more complex but crucial for reliable communication. If we consider distance, classical signals weaken with distance but can be amplified easily. Quantum states cannot be cloned due to the non-cloning theorem, so quantum repeaters are required for long distances. Quantum networking may sound futuristic, but it has several practical applications, especially in security and advanced computation. Quantum key distribution, or QKD, this is the most well-known application. QKD uses quantum mechanics to exchange encryption keys. If anyone tries to intercept the key, the system immediately detects it, ensuring unbreakable encryption. Countries are already experimenting with quantum networks for highly secure communication channels between government facilities. Quantum networks can link multiple quantum computers, allowing them to work together on large, complex problems that a single quantum computer couldn't handle alone. Quantum networks can connect ultra-sensitive quantum sensors for applications like navigation without GPS, precise timekeeping, and environmental monitoring. Despite the excitement, quantum networking faces several challenges. The first one is being with the distance limitations. Quantum states are delicate and can be disrupted by environmental noise. The next challenge is with the quantum repeaters are still in development. Unlike classical repeaters, quantum repeaters are much harder to build. The next thing to consider is with the integration with existing infrastructure. Current networks are built for classical data. Quantum networks require specialized hardware and protocols. When it comes to cost, quantum devices and fiber for quantum communication are extremely expensive right now. These challenges mean that a full-scale quantum internet is still a work in progress, but research is advancing rapidly. The future of networking could be revolutionary with quantum technologies, quantum safe encryption, global quantum internet, and also the impact on industries would be wide. Even if quantum computers can break current encryption, quantum networks provide secure alternatives constituting quantum safe encryption. If we consider global quantum internet, imagine connecting quantum computers around the world, enabling instantaneous collaboration on complex problems. If we consider the impact of quantum networking on industries, it will be helpful in finance, healthcare, defense, and logistics. All of these could leverage quantum networks for secure data transfer and advanced computation. In short, quantum networking is poised to complement classical networks, not replace them. It will become a specialized layer of ultra-secure and high-performance applications. So to recap, quantum networking is about transmitting qubits instead of classical bits. It relies on superposition, entanglement, and quantum teleportation. Its key applications are secure communication, distributed quantum computing, and advanced sensing. While there are challenges, the future looks promising as the research continues. That's it for today's deep dive into quantum networking. If you enjoyed this video and want to stay updated on networking technologies from classical to cutting edge, make sure to subscribe to the Network Fixer and hit the notifications bell. Thank you for watching, and I will see you in the next video where we continue fixing the network one concept at a time. Until then, take care of yourself and have a great day. Bye bye.